In this lab, you're going to be investigating how does the time that you allow a cart to roll affect its velocity down at the bottom. Now, we're going to be doing that by timing how long it takes to travel specific displacements, and then we're going to calculate that velocity in the end. That'll let us get to a velocity time graph, velocity on the y-axis, time on the x-axis there, going along with our question, how does the time that allow an object to roll down a hill affect its velocity down at the bottom. Now, how you do it. Set up a cart on a frictionless track. Make sure you have the magnetic stoppers on both ends so that the cart doesn't go flying off. The carts are expensive. You need feet down at the bottom, and you are going to take the feet on one side and you are going to unscrew them to raise one side of the track. So what you'll notice is the feet actually are adjustable. I can screw it in or unscrew there. So I'm going to unscrew one side as far as I can without it becoming so wobbly or accidentally coming out, because if I keep on going, then I actually can take the foot all the way out. Please make sure that you don't do that and then lose one of the feet. So I take one side out a long ways, the other side I screw all the way in to where I get an angle, but I don't want too steep of an angle, because if I get it too steep, like this is currently at approximately 1 degree, if I get it too steep, it's going to become very hard to time because the cart will get going so fast. So I get the angle of the track. I start my cart from some chosen location. Please be careful. If you come all the way back here and you're using one without a stopper, the magnets in the cart and the magnets in the stopper on the other side, I meant the spring here, but the magnets in the cart and the magnets on the stopper will actually repel and cause the cart to launch forward on you, and you don't want it to launch forward. We're trying to keep it rolling freely there. Likewise, if you do have one with the spring, you don't want to compress it and then actually launch it forward. You want it to start with an initial velocity of 0. So I'm going to pick a spot that's maybe a little ways away from my magnetic stopper here, maybe the 25 centimeter mark. First trial that I'm going to do, I'm going to allow it to roll 20 centimeters or 0.2 meters, see how long it takes to do that. So I'm going to start at the 25, let it go 25, 35, 45, going from the 25 to the 45, that's a 20 centimeter displacement. Start the stopwatch, stop it, and then I do that 5 times. Do it again for 25, going all the way to 40 centimeter displacement. So I'm going 25, 35, 45, 55, 65. Start, stop the stopwatch, do that 5 times, and continue to do that for all 5 independent variables. The time it takes to go 0.2 meters, 0.4, 0.6, 0.8, and then a whole meter. You're going to use that data to actually get your velocity. So now you have your times that you can graph out. You'll take the average of each trial, and then you need to calculate your velocities. Now, velocity is an indirect measurement. Indirect measurements means that you can't obviously directly measure them. Kind of like I can directly measure displacement because I have basically a meter stick on this track, and time is a direct measurement because I have a stopwatch that I can actually use. Velocity, unless you have a radar gun, which that doesn't work on the slow moving cart, or use video analysis, there are some ways to do direct measurements with it, but one way or another, velocity is, for us, an indirect measurement, meaning we have to calculate it, meaning that you need a calculations table like you will see on your lab sheets. So you're going to take the average times, your displacements, and the initial velocity of 0 that allow you to calculate the velocity. Then you'll have the times from the cart's actual movement, your calculated velocities, that then you'll be able to graph out for a velocity time graph. And something about that graph, because this is a constant acceleration, the slope is the same throughout, right? So something about that velocity time graph should indicate that we have a constant acceleration here.